Alright, integrals. Remember, the derivative of t squared is 2t, and this could represent a car moving on the road, and this is the road where your car is moving. This is x of t. Then this is going to represent how fast that car is moving along the way. It's 2t, that's a parabola, so the behavior of your car is going to look like this. And actually this is what the odometer in your car is going to tell you. Odometer, trip meter, distance meter, whatever you call that. At any moment I want to know how far I am from my home, I will look at the odometer, right? Provided that I had set my odometer to 0 when I started off. And that's 2t, that's going to be a straight line, and it tells you the speeds, right? And this is actually what the speedometer in your car is going to tell you. The speedometer. At any moment I want to know how fast I am moving on my bike, I always look at the speedometer, right? In other words, after 1 second, my trip meter is going to tell me I am 1 meter away. After 2 seconds, 4 meters. After 3 seconds, 9 meters away from my home. And this tells you the speeds along the way. After 1 second, my speed is going to be 2 meters per second. Put 1 here, you get 2. After 2 seconds, my speed is going to be 4 meters per second when I am here. After 3 seconds, it's going to be 6 meters per second when I am finally at 9 meter mark. And calculus is about a connection between a function and its derivative. So I have a function, and by the way, we can gather this information from odometer. And then what derivative does for you is it gives you speeds. It gives you speed without you ever looking at the speedometer. You don't need it. You don't have to look at the speedometer anymore. You look for the slopes. You want to find the speed here, you look for the slope. You look for the slope here and there, and the slope is 2t. So if you put t equals 3, this slope is 6 meters per second, and this is 4 meters per second, and this one will be 2 meters per second. So it does that. Now suppose I have this speedometer, but odometer is broken. I have this function, but distance function is lost. Can we now go back, having the information for these speeds, can we find out distance traveled? And the answer is yes, we can do that. We do integrals. We call this process going back, taking antiderivatives. So when we take the derivative of t squared, it gives me 2t. But if I want to come back, we use a new notation, this sign which we call integral sign, dt and 2t, then this gives me my function back, distance function. And so for derivatives, we look for the slopes to these curves. It gives you speeds. For integrals, we look for the areas under this curve, and it gives you the distances. I will get back to this point why we look for the areas under the curve and how they give you the distance traveled. But for now, I just want to show you that it works. Looking for the areas under the curve is going to give you the distance traveled. So if you want to find how far you have moved after 1 second, we look for this area. And this area looks like a triangle's area, which is length times breadth divided by 2. So you think of this length as you think of this dimension as the length in time dimension, and you think of this as the breadth in velocity dimension. So 1 times 2 divided by 2 gives you 1 meter. Right? Now if you want to find how far you have moved after 2 seconds, you find this area. 2 times 4 is 8 divided by 2 gives you 4 meters. Now you want to know what happens after 3 seconds. Well, you find this area. 3 times 6 is 18 divided by 2 gives you 9 meters. So yes, it gives you the speeds. It gives you the distance traveled. Right. So we are looking for antiderivatives. First I want to talk about that, then I will get back to this idea that the area under the curve gives you distance traveled. So if I have a function t to the n and still the velocity function v of t, then what is the antiderivative of it? What is the integral function? Well, whatever that function is going to be, x of t, whatever that mystery function is going to be, when I take that and I do the derivative, it should give me back my t to the n, right? It's calculus, they are connected. This function to its derivative, or you could say this function to its integral. They are all connected. And so, what is this function? Well, that's easy because that's a polynomial function, so I can make a guess what that could be. If I take a function t to the n plus 1, and now I take the derivative of it, n plus 1 will come down here in front, so it will appear here, n plus 1. Then I have to subtract off minus 1 in the exponent, then you are left with t to the n. That's what you see here, but you are having this extra term, right? But I do not want that, so I better off divide by n plus 1. Now it's fine. Now take the derivative, n plus 1 will come down here, they cancel each other, so this disappears, and now you have to take minus 1 from the exponent, so you are left with t to the n, and that's what you see here. And keep in mind, you cannot take n equals 1. Take n equals minus 1, put here, you get 0 downstairs. Oh my goodness, all hell breaks loose. Don't do that. Don't take minus 1. So this is the antiderivative of that function, or is it? Because now I could have added here a constant of my choice, and it is still fine, because now I take the derivative of this function. This one is surely going to give me t to the n, and the derivative of a constant is going to be 0. We are interested in changes, and constants do not change. And so this constant could be pi, it could be e, it could be minus 1, it could be 7, Cristiano Ronaldo, CR7, right? And so this function can have infinite number of antiderivatives, each corresponding to a different value of a constant. And this constant can also be 0. Right? And I can show you that on graph. If I take x of t, still the parabola t squared, it goes like this, and let me extend that into negative direction too. And now if I add, let's say I add 7 to it, then this curve will jump up by 7, right? So this is 7, that's what changes. So this point jumps up here by 7, and this point does the same. But it doesn't change the fact that the derivative at this point, the slope here and slope for this function are going to be any different. No, they are not going to be different, because what you just did is you just take a function and you have displaced it from the origin by 7. Or you can say this function represents your friend's car that starts from here, and this is your car, and both the cars have the same behavior. Both the cars going to have the same speeds along the way, right? It's just that your friend's car is always 7 meters ahead of you. So this function, these two functions are going to have the same velocities, which is 2t. Or you could take -1, then it just comes down. That's the difference. So now I want to talk about why looking for the area under the curve gives you distance traveled. And for that I need a function. Still, the velocity function, and this function goes like this. It goes from 0 to 8 seconds, and this peak value is 10, and this will be 5 meters per second. And you are being asked, having this information for these speeds, can you find out the distance traveled? I don't know, but this problem would have been ridiculously easier if you had given me a constant velocity function. Maybe that constant could be 5 meters per second, and it goes from 0 to 8 seconds. Then what is the distance traveled by this car? It is going to be v times delta t. Right? You are moving with the speed of 5 meters per second, and you have been moving for 8 seconds. Each second you cover 5 meters. After 8 seconds it is going to be 40 meters, right? And you think of this as the length in time dimension and this breadth in velocity dimension. Then v times delta t represents this area under this curve. And it's really funny that this area has the unit of meters. So it confirms that we have to look for the areas. We have to look for the area under the curve. It gives you distance traveled. Right? So what is that? Well, we know how to handle constant velocity function, but we got no damn idea how to deal with continuously changing velocity function. So finding the distance traveled from this curve looks like a nightmare. So let's not do that. I cannot find you the exact distance traveled for now, but what I can find you is the approximate distance that you are going to travel, and I will use the idea of constant velocity function. And let me first divide it into, this is 4, 5, 6, 7, 3, 2, 1. What I'm going to suppose that for these intervals, velocity stays constant. What I mean is, at time t equals 0, velocity is 0. And I am going to assume that it stays 0 for 1 second, then it jumps up to this value, whatever the value you have on the original graph, then it stays constant for a second, jumps again, stays constant, and then jumps again, and now it is going to jump down, and also here, like this. And let me just now connect them. Now you will see why in a second. It will just, alright, it's done. Well, it's true that I cannot find you the area under the original curve, but I can find you these areas of these rectangles. I can find you for this one, the area for this one, and so I cannot, all I have to know is this velocity for this interval, right? the velocity for ith interval of t, whatever that is, looks like it is 9.5 meter per second, and delta t is 1 second, right? Then this area is 9.5 times 1. It gives me this area. So Vi of t times delta t is going to give me this area. And I can do the same for this one. All I have to know this velocity. V of looks like it is the 6th interval. I don't know, maybe 6th. Whatever that speed is, looks like it is 6 or so. So, alright, 6 times 1 gives me the area for this one. And I can find the area for this one, here, there, this one. And I add them all up. So I run a summation from I1 to n, and in this case n is going to be 8. And so I couldn't find you the area under the original curve, but I have found you the area under this curve that you see, right? That's what we have found, and this gives you the approximate distance that you are going to travel, right? You might have noticed that we are getting this extra area, right? And we are gaining some of that extra here, and we are losing some of that area here. Same here, and we are gaining some of that here. Is there a way, can we do something about those extra areas and lost areas? Yes, we can do. What if I take my delta t, that interval, to be 1/4? I let the speed to be stay constant for 1/4 of a second. So let me just divide it into 4 parts. So my velocity stays constant for 1/4 of a second, then it drops, stays constant, drops, stays constant, drops, like that. And now I can find you this area, the area of this thin rectangle, and then this one, and the area of this one, right? And I have to do it here too, right? And in the end, I have to add all of those thin areas. And look, this extra area, some of that is disappearing, right? Look at that. And it will happen here soon. So I hope you can see it already, what I am trying to do. What if I take my interval to be 1/8 of a second? Then you are going to see that a big change. I have to divide it into 8 parts, right? I think they are 8 already. So speed stays constant for 1/8 of a second, goes up, stays constant, like that. And look, I have to find this thin area, rectangle, and this one, right? And look, that this was the lowest area that we couldn't consider, and now we are gaining that, right? And you have to do the same idea here. I have to divide all of these rectangles in 1/8 of a second, and then you will see that that some of that extra area is getting disappearing, and some of that lost area is coming back. And so I hope you can already see the big picture. What I'm going to do, I'm going to let my delta t to approach 0, because as we let our delta t to be shorter and shorter, this approximation for the distance traveled is getting better, and that's the idea. So what happens when as my delta t approaches infinity, I have to divide this rectangle into infinite parts. So those thin rectangles are going to be too thin, that they are going to appear like lines. And so you are no longer going to see these staircase-like of shapes. Rather, you're going to see something smooth. and now this area you can find that, right? And you have to do the same idea here. You're going to see this becomes smooth and you find that area, right? So what we do is we limit as delta t approaches, oh excuse me, we let delta t to approach 0, right? In my enthusiasm I wrote infinity, but it was 0. We are getting shorter and shorter, right? So it is really 0. Then those lines, those seen rectangles are rectangles, right? Are going to be infinitely large. And so what you're going to see is, as you let delta t to approach 0, not infinity, 0, this area, X-ray area is going to disappear. And those lost areas are we are getting them back. And so this becomes exact area that we were looking for. So this is the area that we were looking for, and it gives you the exact distance traveled, right? And we write this equation in different language now. We say the integral sign, and we go from 0 to 8 of that v of t times dt gives me the area under the curve, right? We say go from 0 to 8 and add all of those areas of those thinnest rectangle, all of that, and then you get this area, right? But what is that? It is the area, but what is that, right? It is the infinite sum that I have to deal with. Look, infinite sum. So I'm not going to do an infinite sum. Is there a better way? And yes, there is a better way, and this is where calculus comes in. Remember, this velocity function is deeply connected to its distance function, x of t, right? And this is going to give you the exact distance traveled because it is a distance function. And I had it last time in my last lecture, and it goes like this, from 0 to 8 seconds. So to find this area, which is the exact distance traveled from 0 to 8 seconds, you have to find the position at time t equals 0 and the position at time t equals 8. This gives you this distance, right? So you have to know the position at time t equals 8 minus the position at time t equals 0. Then this difference, this height, is going to give you the distance traveled. Simple idea, because they are connected. That's the, you are looking at a beautiful thing that we had to find this area, and then somehow we were getting an infinite sum, and then we used calculus to simplify that. It becomes so simple, right? And so if you want to find the area, the distance traveled between a seconds to b seconds, right? So you have to find this area now to find the distance traveled, this area. So this is going to be point A, point B. All you have to know is this position at X and position at B. It gives you this height difference. So we go from A to B, right, for that area, and so this becomes the position at B minus the position at A gives you the distance traveled. This gives you area, this gives you distance traveled. So that is this, right? Calculus connects this function to this one. It also goes back. So they are connected, right? And what you are looking at is the fundamental theorem of calculus. And now let me write this fundamental equation, the theorem, in general form for any function. Right? So if I had a random function f of x and I integrate it from a to 0, a to b, it gives me its antiderivative function that I have to evaluate, capital F, evaluate it between point B and point A, right? That's the fundamental theorem of calculus that you are looking at. And remember, the derivative of capital F of x has to be f of x, small f of x, where capital F of x could represent temperature as a function of x as you move along in the x direction. Then this f of x is going to represent the derivative of that in the direction of x. It is going to tell you how fast, how quickly the temperature is changing as you move along in the x direction. Right? We call this temperature gradient in physics, temperature gradient. And this f of x could represent electric field in the x direction. So if you know electric field everywhere in the x direction, you can find the potential difference between point B and point A. So that's what it tells you. That's the fundamental theorem for you. And there's one last thing that I have to discuss. And that's the area, that's the idea of negative area. What is that? Now, suppose that your velocity function had negative values. And just let me give you this function. Still the velocity function, v of t, and it goes like this. And it is really the cosine of t, right? Most of you might know it. Then this area above this curve and under this line, this area is considered as negative because the velocities are going to be negatives, right? Negative values. This is 0 and this is where they will be positives, right? And you can also see that in terms of those thin rectangles, this area, all you have to know is velocity at this time times dt gives you this area, dx dt, not dx dt, dx. It gives you that little bit of distance traveled. So v of t times dt is going to be negative because v is negative. So if I integrate it from point A to point B, this area is going to be negative because all the v's between this point and this point are negative, right? And so, hold on a second. And so, by the way, what is the meaning of having negative velocity? If, let's suppose, and not suppose, if we call this direction to be positive, then if you move in the same direction, we say you have positive velocity. But if you move backwards, we say you have negative velocity. So if you move from here and you move forward, then you put your car in reverse and you go back and you end up here, then we find this distance. Actually, we find the displacement. And let me amend my words now. When I was saying that I am going to find you the distance traveled, I was actually finding you without telling you the displacement. Right? And you can also see that in terms of its partner function, the distance function, right? And let me draw these to guide my hand to make you a better curve. It is going to look like that distance function, that derivative function is going to look like this. And this is the really sine of theta. The integral of cosine theta is sine of theta. Or you could add here constant too, but I'm not going to need that. If you want to do that, go ahead. But whatever follows wouldn't change. And so, you can look why this is called negative area, because it means you are moving backwards, right? Because velocity is negative. So if you see, at this time, at the distance function, you are here. At b second later, you are here. So you are here, right? And you end up here. So you are going down. You are moving backwards, right? And now, actually, you are going to see it why this is considered negative. This is going to be positive, and this area is going to be negative. So if I add this area with this one, it should give me 0, because you are here at time t equals 0 and you end up here, looks like it is pi after pi seconds, and so I have to find you this height difference, x of b minus x of a, which is really the x of pi, right? This is b for now, pi, and this is 0. So what is really happening is you go up and you are now coming back to the same position, because you have to find the height difference, right? And so what is the height difference between them? So what is the displacement, right, between those 2 points? You go up and you end up where you started. What's the displacement? Right, 0. Alright, this is it. I will see you next time.